Okay, well, the clock has just ticked over, so I'm going to start. And in fact, I will start with my actual title slide. You may recognize this. We'll get to that a little bit later. But first, just to introduce myself, I am Phil Nash. Many of you may have seen me giving talks like this before, but you may it may be new, the logo that I've got associated with my name, because I've recently changed my position. I'm now developer advocate at SonarSource, still developer advocate, so I still do way too many talks. I'll talk about that in just a moment. But yeah, I'm also still Phil_Nash on Twitter. So you can follow me now. You'll see that again right at the end if you need to unfollow me by that point. So this is Zen and the Art of Code Lifecycle Maintenance. I'm sure for many, hopefully most of you, you'll get the reference. There is a book with a very similar name. We'll see that a little bit later. But first of all, I mentioned that I do way too many talks, and actually I'm going to start on that just for a bit of context. So I actually keep track of them all on my website, levelofindirection.com. And I was just looking at this recently. Since 2015, I've done quite a few talks. I hope you're getting all this. I've actually done 114 talks in that time. Now, many of those are repeats or different talks on the same subject. And I was actually looking back over this and realized that I can actually group 4 major themes from most of those talks. Obviously talked a lot about testing. For those of you that know me, you'll know that's a big thing for me. Functional programming. I've actually done my longest run of talks on functional C++ for fun and profit, but a few other talks as well on similar subjects. A pair of talks I've done on error handling quite a few times. And there's just one talk, I've done it a few times, on simplicity. That one turns out to be probably the richest vein of material that I keep mining from for some of my other talks, and this is one that's going to be no exception. But you notice the way I've drawn those bubbles there, there's some overlaps between them. And I found that in the material as well, that there is overlap between all of those things. This talk is going to be about the overlaps, not just between these previous talks, but as we'll come on to in a moment, different aspects of software quality. Now, as I was looking back, even after grouping these into these 4 main areas, I realized that even then there was a common thread between those 4. And that common thread, well, I've already mentioned it, is software quality. So again, this talk is going to be about software quality. And I'm going to distill out a number of properties, 3 qualities, as we'll see in a moment. And again, we're going to look at the intersections between them. That's where I want to be maybe slightly different in this talk. I'm not just going to discuss the qualities themselves. We will discuss those, but I'm really interested in the intersections. So really we have to start with a question. What is software quality? This turns out to be quite tricky. Now, there is a blog that I sometimes follow, Shape of Code by Derek Jones, and he's written a book on evidence-based software engineering. And there was a post from earlier this year where he talks about the aura of software quality. Now, towards the end, one of the final paragraphs there, I like the way he starts this. People in industry are very interested in software quality, okay? And sometimes they have the confusing experience of talking to me about it. I might give you an idea what his views are on software quality. And a little bit further down the same paragraph, software quality is a meaningless marketing term. Okay, not a good start for a talk on software quality. But he did say that people are very interested in it. And I'm sure if you've come to this talk, hopefully you are interested in software quality. And of course, we have this. The only valid measurements of code quality, WTF per minute. We all know this one. And it's a fun cartoon, and it's funny because we can relate to it. Software quality definitely has this aspect of, you know it when you see it. The trouble is, it's really hard to define it. We'll come back to that in just a moment. Actually, just as a little amusing aside, when I was pulling this cartoon up, I ran it through iOS's live text that lets you actually select text from an image, including handwriting, and it didn't quite get it right. Now, I'm not quite sure what to read into that when it comes to software quality, but as I said, little aside. Now, I said that it was hard to define software quality. Derek Jones said that actually everyone seems to have their own definition of software quality. That's really the problem. And we've also said that most people have this idea that they know it when they see it. Now, that's interesting because there's this book, and maybe this will look familiar now, Zen and the Art of Motorcycle Maintenance. I'm sure many of you have read it. If you haven't, maybe you should. So it's not a book about programming. If anything, it's a book about philosophy and metaphysics. Really, it's about quality. And for a large section of the book, he talks about how quality is undefinable. You can't pin it down, but people say they know it when they see it. He also then tries to split it into what he calls classical and romantic quality, the sort of the how things work compared to the how they look or how they're used. And actually, there's a follow-up book, Lila. Not so many people know that one. Definitely worth a read as well. Where there he actually splits quality into static quality and dynamic quality. Interesting, static and dynamic are terms that we are used to juggling as developers. So there's this idea that quality in general is hard to define. So it's not just software quality. It's not just us that has the problem. Derek Jones earlier said that everyone seems to have their own idea what software quality is. So I looked up on Wikipedia for some definitions. And you'll find quite a few there. I've just put out a few select ones. Obviously, these are all supporting my narrative here, so do consult the page yourself. There is a link at the top. Actually, all of the links for all of the references, I will provide you a single link at the end that will get you to all of them. So don't worry about trying to keep track. So on the Wikipedia page for software quality, most of the, I won't read them all in detail, most of the quotes there really are talking about the external quality of software, like you as a user or a customer or an end user might see, how well does it actually serve the purpose that it was designed for? And that's obviously very important, arguably the most important thing. You might be surprised that I'm saying definitely the most important thing. There's a counter argument to that we'll come on to, but definitely a very important thing. Although I do like the quote right at the end from Jerry Weinberg, quality is value to some person. So it's slightly more generalized than the others. Not talking about customers or users, but just it's value to some person. Doesn't matter who that person is. And then there's that word value there, ties us back again to this book, Zen and the Art of Motorcycle Maintenance, because the subtitle there is an inquiry into values. You could argue these are different types of values to what Jerry Weinberg's talking about, but we're definitely in the same sort of ballpark with this. We're in this very sort of philosophical area, so it's a bit dangerous. So let's refocus back into what's very specific to us in, or generally, information technology, software development, you might say. There is a consortium, or consortium, depending on how you like to pronounce it, for information and software quality, CISQ. Now, if you went to Anastasia Kazakova's talk earlier in the week, I think she also quoted from them, they had their own definition, again, of what software quality is. So really bearing out Derek Jones that everyone has their own idea. And on their main page, they talk about a number of things, but particularly structural quality is what we're mostly interested in. It refers to the software's security, reliability, performance efficiency, and maintainability. So now we're getting to something a bit more concrete. Here's a list that we can work with. Let's actually make it a list. Security, reliability, performance efficiency, and maintainability. They sound like promising suspects, I think. You'll probably agree, yeah, get these right, your software should be good quality. Now, independently, before I looked up this page, I came up with my own list and I compared it against this. And the core of it, I think, is very comparable. Not an exact mapping, but pretty close. I think the main difference is the first two. Instead of security, I got correctness. So I'm thinking much more at the code level rather than the system as a whole so much, although they're very interrelated. I would argue that if you get correctness right, which is really the absence of bugs, you're a long way towards security. Not all the way by any means. There's a lot more to security that's actually outside my domain, so that's why I'm not going to talk about it. But it's a big part of it. If you can get your software to be bug-free or as close as possible to it, you're going to be a long way to having secure code as well. Now, reliability, well, we both got those. I may have a slightly different take on it. I'm going to dig into that in a bit, but we got the letters right at least. Performance efficiency was amusing because I independently came up with performance/efficiency, two slightly different but very related things. So I'll take that one. And for maintainability, I've got malleability or evolvability. And I wasn't quite sure which, they both sounded a little bit awkward, so I put both of them there. Again, they've been slightly different things, but they're in the same ballpark, and they're definitely related to maintainability. But not just maintainability and just keeping things going, but maintainability in terms of how we're going to respond to change, how we're going to change this, build new features over time. So maintaining it at that level as well. So that was the core of my list, corresponding quite well. But I'm going to add two more. The first one, just going to add to the end, I'm calling it reasonability. The ability to reason about your code. Sometimes we will call this readability. It's not quite the same thing, but yeah, it's the ability to look at the code and know what it does as easily as possible. You know, the harder you have to think about it, the harder it is to reason about the code. We'll dig into that later as well. And then I'm also going to bring in what I'm calling applicability. And this is really what all those systems theorists were talking about on the Wikipedia page. And how applicable is it to the task that it was designed for? How does it meet sort of end users' needs? That seemed to be a little bit missed from the CISQ list, mostly because, as I say, it was talking about structural quality, so that was one of their other lists. But let's bring it in to make that a bit more complete. So now we have this set of 6 qualities. So we're talking about software quality, but we've actually got 6 qualities, plural now. Now, whenever you get a list of things, it's always tempting to try and see if you can get an acronym out of it. And I'm definitely no stranger to that. So I took this list and I had a go. Unfortunately, if I just take those letters, the best I could come up with was Mr. Crap. And I wasn't too happy with that. So I thought I had another go. Now, there was a couple of items in there where I got 2 alternate names, like performance and efficiency, or malleability and evolvability. If I take the second 2 from those, a little bit more promising. Switch those around. I managed to get career out of that. Now, I've never really considered myself a career programmer, but maybe now is the time to start. Can be useful to have an acronym just to help you remember the leading letters at least, and maybe you can remember the qualities from that. So I'll leave that with you, whether you want to run with it. But I mentioned earlier that having got this list of qualities, I'm really interested in the intersections between them, where they meet, where they overlap. So that's really what the meat of this talk is going to be about. So now we've got that list, let's have a look at some of those intersections. The first one I want to look into is the intersection between correctness and applicability. Now, you might think of this along the lines of doing the right thing versus doing the thing right versus doing the right thing. We usually say it the way around. And in fact, there's quite a well-known quote from, again, another systems theorist, Russell Ackoff. The righter we do the wrong thing, the wronger we become. When we make a mistake doing the wrong thing and correct it, we become wronger. When we make a mistake doing the right thing and correct it, we become righter. And here's his conclusion. This is the bit that everyone remembers. Therefore, it's better to do the right thing wrong than the wrong thing right. Or sometimes it's worded as do the right thing first and then do it righter. And this has sort of been ingrained in many of us, particularly anyone that comes from a more business background, that you do the right thing first, and then you'd actually work on doing it righter, getting all your best practices and improving the quality of it. Which seems to make sense, because if you're doing, no matter how well you're doing it, if you're doing the wrong thing, you're just doing it faster. But there's a bit to this quote that people usually miss, because he follows immediately on by saying, this is very significant because almost every problem confronting our society is a result of the fact that our public policymakers are doing the wrong things, are trying to do them righter. So, as I say, Ackoff was a systems theorist, and he was really talking here about society and policymakers. Now, that doesn't mean that this doesn't apply. I'm not saying that. But I'm just saying we should be careful about directly applying this. Sometimes the details do become important. And particularly when it comes to software delivery, there are some different factors involved which may actually change our thinking. Now, there's a talk from Alan Kelly. I tracked it down to 2013. I didn't find a more recent one. There'll be a link to the video in the references. It calls it do it right and then do the right thing. So a reversal of Ackoff's approach. In fact, he quotes Ackoff in the talk. So he says that it's only by actually doing that you know what the right thing to do is. His main premise in the talk. In other words, you have to actually start doing things before you know what the right thing is. And the righter you are doing it, the more you're using best practices, particularly modern best practices in software development like TDD, and we'll talk about that later. Then also, the more likely you are to be able to change course to do the right thing as you discover what it is. Was his main point in this. And he wasn't 100% sure about this. All the evidence seemed to be leaning in this way, but he actually presented the talk as an open question. It's got a question mark right there in the title. Just a couple more slides from his talk, actually, because it's really interesting. And I do encourage you to watch it. He presents something called the alignment track. This is based on a study that he quotes. And you can see I've got a quadrant diagram there. And he's saying that most companies are in that red quadrant in the bottom left corner, the maintenance zone, where they're not particularly effective and they're not doing the right thing. Nobody wants to be there. That's where most businesses are. Obviously, everyone wants to move towards the yellow quadrant in the top right, IT-enabled growth. Very few companies are there, but where they are, they're effective at doing the right thing. Sounds great. But then there's these two other quadrants. There's the alignment trap quadrant, where the slide gets its title from, where people are doing the right thing, but just not very effectively. And then the bottom right, the well-oiled IT, they're not necessarily doing the right thing, but they are doing it very effectively. Now, if you look at the figures associated with it, I won't break them all down, but Alan goes into it in a lot of detail. But you're much better off in that green quadrant in the bottom right, where not only are you already doing much better, but it's much easier to move from there into the yellow zone. As I say, I'll let you watch the talk to get the detail from Alan, but it's a really interesting way of thinking about things that challenges what we may have just taken as a truth before, that we should do the right thing and then work on doing it right. He also uses this analogy of ready, fire, fire, aim, fire. So only once you've actually taken a few shots do you really know what you're aiming for, and then you can hit the bullseye. And really what he's getting at here, or what he sums it up as, is rapid iteration combined with learning. And learning is really the key here. So rapid iteration on its own is not going to get you anywhere, but that learning is what will get you focused on the target once it becomes apparent. And very often, there's no way you can see it at the start. So there are some things that will help to enable that we'll talk about later. But I thought this is a really interesting treatment of this intersection between correctness and applicability that reverses the traditional view on it. So do watch that talk, recommend it. I'm going to move on to the next intersection, this time between correctness again and reliability. Now, by reliability, I really mean how well covered your code is, particularly things like error paths or unexpected paths. So starting by talking about code coverage, if you've ever tried code coverage before, you know, it mostly boils down to line or statement coverage, depending on which coverage tool you're using. And if you've used TDD, test-driven development, you'll know that if you follow TDD strictly and 100% on your code base, you should automatically end up with 100% line or statement coverage, just by the nature of the way TDD works. So yeah, having a coverage tracking tool, if you're doing TDD, well, it may be useful, it may show you if you've missed something, but generally, you should always be at 100%. Now, of course, you know, very few of us are able to do greenfield TDD, but if you are, that will give you 100% line coverage. And that means that all your code is completely covered, doesn't it? Well, no, obviously, line or statement coverage doesn't cover all possible paths through your code, all the different values that are involved. And that's usually where all the problems are hidden, particularly on those hidden error paths. Think of particular things like exceptions. Very often not evident in the code, and many coverage trackers won't even show you those. So yeah, a tool that will track your line or statement coverage, we have those, they're great. You should try them, but don't trust them too much. But tracking your data coverage, for want of a better term, is, for anything non-trivial, pretty much impossible. Now, if you're doing TDD, that will give you good coverage, data coverage of all the values that you thought were significant. So a big part of TDD is an evolving design. So what I like to think of as the contours of the design are those sort of boundary conditions that we think about. And the TDD process sort of helps us to think about some of these, like zeros and int max and things like that, those obvious boundaries. There'll always be some that you've missed, though. And TDD is not a good tool for getting at those. So I should have built that up already. So a tool that's much better at covering the paths you didn't think about is something called property-based testing. Now, if you've used property-based testing, you'll know that this works much the same level as unit testing, but rather than working with specific examples of values and calls, it will generate randomly the actual data. And then you can reason about properties that will hold for all values, or sometimes you can carve out domains of values and test within those. But the best ones are ones that apply to all possible values. If you can find a property that holds all values, then you will use the framework to generate the values, let's say randomly. Now that randomness can be seeded, so if you do find a failure, you should be able to reproduce it as well. But that means every time you run it, you're going to cover a bit more of the domain, a bit more of, say, the range of an integer, or if you've got the string generators, different types of strings, different lengths of strings, whatever it is you're dealing with. Property-based testing will find the things that you didn't think of. That's its real strength. You may not find it immediately because you'll only be working with a limited set at a time. But over time, it's going to explore more and more of that space. Somewhat related to that, but at sort of a higher level, more sort of from the outside, is fuzz testing. Again, generating random inputs, but maybe weighted more towards sort of known problematic values, and particularly targeted, maybe more at the security angle, maybe even like SQL injection, but generally things that are known to be problematic, plus lots of randomness. A little bit more out of my depth on that, but I know that that's definitely an approach that can give you a lot more coverage, particularly in terms of how reliable your code is, talking about the reliability. And don't forget manual testing. So we want to automate as much as possible of our testing, but there's still a space for manual testing. Again, for finding the things that you didn't think of as a developer, someone whose brain is more tuned to how you can break things makes a great manual tester. That they're indispensable. So there's still a role for that, just not the things that you're going to be repeating. So we talked about coverage. We said, yeah, line of statement coverage, that's a known quantity, and TDD will get you pretty much all the way there. Whereas data coverage, that's a bit harder. Property-based testing will help, as will fuzz testing and manual testing. I mentioned error paths earlier, in particular how they're often hidden, particularly thinking of exceptions there. Or even if they're not hidden as such, thinking, for example, of error codes, maybe they're easily ignorable, so that's a different way of hiding them. So we have no discard now, which we should definitely use if we're dealing with things like error codes, but we have to work with code that was written before we had no discard. Now, there's really two types of error paths that I'm thinking of. I'm going to divide them up into what I call IO errors, sometimes known as disappointments. And these are things that, well, we expect they can happen just as part of the normal running, usually coming from sort of user inputs or from file or over the network or somewhere outside your code. Values will come in, they need to be validated. And if they don't validate, you've got to handle that somehow. It's disappointing, but you should write your code to handle that. That's fine. And then you get logic errors. This is really more the domain of contracts. Now, we're not going to talk so much about contracts relating to the proposal that was going into C++ 20, was taken out. It's being talked about again for 23, may miss that as well. We should get it in the language at some point. And that's quite a rich set of support for this, this type of error. We can get most of where we need to with just an assert. We'll obviously hope for full contract support at some point. But when I'm talking about contracts here, I'm really talking about the implicit contract, the contract that you, as the writer of your code, have with who's going to be calling it. If you can capture that in contract syntax, that's great. If you can capture at least some of it with assert statements, that's good for now. So these are logic errors. Now, it's been said that std logic error is itself a logic error because exceptions really belong to the first category, those IO errors. Things that, well, you should handle them. They can happen, but you'd rather they didn't. Whereas logic errors, really, they should ideally abort your code, or you should assume they can't happen and they'll just be left as undefined behavior. So that's really what we're talking about here. Let's actually look at a bit of code just to put this into a bit more perspective. So simple function to just convert a string to an integer. And we're using a string stream just because everyone should know how that works. Not the best way to do it. But you should see where we're going with this. Okay, so we've got an integer there. We write the string into the stream, and then from the stream out to the integer and return the int. Fine. I can call that with something that's not an integer. What happens? Well, when I ran this, I got 0. And my reading of the standard, I think that's guaranteed. I'm not 100% sure because you have to read through quite a few layers to really get to the bottom of that. But I think that's guaranteed. But that's not great. That's really just because we started off with 0 before we've evaluated anything, and then we get to the first non-numeric character and we bombed out. What we missed, of course, is handling errors coming from string stream itself. And we can test that with .good or conversely .fail, but that's not all the cases. So I think .good is the best approach. And in the else case, well, we have to do something else. We could throw an exception. Now we have to think about the interface of str to int. Is this something where you're going to just try to convert something, and if it doesn't work, then we'll do something else instead, so more of a control flow thing? Or is what we're passing to it normally expected to be an integer, but sometimes won't be? That's going to impact the way you deal with it. So an exception here may be an appropriate choice. More likely, you're going to want to use something like std optional, where we return the value if we have it. Otherwise, we return a null optional. It's almost what optional was made for, you could argue. It's not really error handling. It's just a case of whether we had the value or not. Great, okay. And we can call that with some code like this, where we get the optional out. We can test it against Truvy, and if we have it, we can dereference it and get the value. We all understand this. I think most people now have worked with std optional, know how it works. It all makes sense. It's got this pointer semantics. There is a little bit of a problem, though. This is better than some things, but you still separately got to test whether the optional has a value, and then separately from that, dereference it. You can easily get into a situation with dereferencing without checking, in which case you're leaving yourself open to, well, what you really want to do is combine those two operations into one, ideally have it done for you. In C++23, we're going to get the so-called monadic extensions to std optional, which will allow us to use things like .map and .else, in which case we pass a lambda to them. And notice now, with map, we're past the already dereferenced integer. So we can't go wrong with that. We're either dealing with an optional or an integer. If we're dealing with the integer, we've got it. It's safe. And then we can use or else in the other cases. And there's also and then as well if we need to follow on with further optionals. So that's been adopted into 23. So we can look forward to that. Great. That's a good way to deal with this sort of thing. There are other things that we can do. We can just use error codes. As I say, ideally with no discard. We can use std optional. We've had std error code in the standard since C++11, but it's way underused. Not appropriate for all cases, but if you're going to be using error, just normal error codes like an enum or something, consider using std error code instead. There's boost outcome if you're using boost, which is sort of part way between something like std optional or std expected, which we'll talk about in a moment, and exception handling. And possibly in the future, not standardized yet. I mentioned the std expected already. I go into this a lot more in my error handling talks. Possibly, maybe less so now, the so-called static exceptions, the P0709 paper. As I say, my error handling talk, I go into this in a lot more detail. I'm just going to touch on it lightly now. Just to say, these are the way that we deal with those disappointments, the I/O errors. And we should be paying attention to them. We should use things like no discard or optional or expected if we have it to enforce in the language what we need to do rather than leaving it to chance. Like raw error codes in enums, easy to ignore. So if we can use the language to force us to consider these reliability issues, this can improve the quality of our code. Okay, the flip side then is those logic errors that we said are the domain of contracts. Let's have a look at a slightly different example. Say you have an integer that represents a month in a year, and we want to convert it to a string. Now, the implementation, not important. It could be a switch statement or a map or something else. But yeah, given an integer, it's going to give you a string. Now, clearly, this is only valid for integers between 1 and 12, or is it 0 and 11? Well, that has to be they're written somewhere. There's an implied contract either way. But given one of those valid integers, then it should always give you a valid string. What happens if it doesn't? Well, before we get to that, let's just take a little bit of terminology here. The integer that we're passing into it has what we call a range. That's all the possible values that an integer can be, which for a 32-bit integer is the 4.5 trillion values. Quite a few more than the 12 that we know are valid. Now, this function in its contract has a domain, the values for which it is valid, which we expect are between 1 and 12. Now, when there's a difference between the range and the domain, that's when we have an implied contract. Now, what can we do inside this function? We could do what we did before and just do a test and throw an exception. The trouble with that is you're always going to pay the cost of that check, even if you know that it's valid, and you may end up checking multiple times. Whereas we would expect to always be giving it a valid integer. So we could write an assertion to say this can stand in for a more fully fledged contract support. But now we've stated that contract in an assertion, and hopefully in our testing, we should whittle out any cases where we're passing something that's not been pre-validated as a valid month. Okay. We could separate that check out to a separate function. So we can say, is this integer a valid month? And now we can use that in our assertion. And anywhere that we need to pre-validate before calling it, we can use the isValidMonth function. Great, now we just localized in one place what it takes to be a valid month. That's a good start. And here's some code that may do exactly that. Now you may decide that, well, I'm doing this a lot. I'm converting these month numbers to strings and I'm always having to check. It's a bit tedious. So maybe you'll write a function month for string checked that internalizes that check as well. Throws an exception if it's invalid. Okay, you can do that. You may want to switch that round so that it's the unchecked one that gets the longer name. And now what you've done is you've made the one that's easier to call, because it's got a shorter name, arguably slightly safer. Now, I say arguably, there are disagreements on this, and it depends on all the context surrounding it, but you're probably more likely to detect errors this way around than the other, but some people will disagree with that. Really what we wanted to do was just constrain our integer to values between 1 and 12. Now, interestingly, on the Wikipedia page for the Ada language, it has an example for bounded integers, which Ada has built into the language. And the example is date types. So it has a month type there that's in the range of 1 to 12. That's enforced by the language. So it does it all for you. Of course, we can do something similar. We could write a simple month class, for example. You might want to make it more sophisticated than this. You can also use a bounded integers library. But if you wanted to make it very, very specific, let's go with this. So we hold the month internally. The constructor will check that the month is actually valid. We can use our isValidMonth function. In this case, it's going to throw an exception. Okay, didn't we say that we knew we were going to have valid dates most of the time, so why pay the cost of that exception? Well, first of all, this will actually push the boundary condition to much closer to the point of any I/O that you're doing, ideally. If as soon as you know that this thing represents a month, you put it into a month class, month object, you know from that point on, it's valid. And you can use it for your month for string function. You know that you're always being passed a valid month. So we're going to do that check once. But of course, you may have an integer that you still know already is a valid month. No problem. We can add another constructor. This time, because it's constructors, you can't give them different names. We could use a static method, but one nice way is to use a tag type, so just an empty type with a name. I called it unchecked tag in this case. It's a second constructor argument, just to distinguish between the constructors. Now, if I pass it unchecked tag, then I know, well, this is meant to be pre-validated, so I can treat this more like a contract and do an assert. And I can construct them something like this. So again, the one that's easy to construct is the one that's doing the validation in the constructor. If I know that I've got it pre-validated, then I can say, yeah, I know this is safe, use the unchecked tag. Again, your preference may be to do it the other way around. That's not necessarily wrong, and there are arguments both ways. The point is you're making it clearer in the code what your expectation is regarding these values. Is it something I know, should be pre-validated. So if I get it wrong, then it's a logic error. It's a bug in the code. Or is it something that's come from an untrusted source, usually from I/O or something like that, in which case I need it to be validated. So there's a few different ways to do this, but the key is the reasoning about it. First of all, deciding which it is you're dealing with, and then making that clear in the code. And again, by using types like this that encode in the constructors the validation, you're pushing the validation as close as possible to the boundary. So you catch them as soon as possible. And then for the rest of the code, you can assume that things are valid and they've been pre-validated, and use the type system to enforce that. Again, we're working with the language. So I'm going to move quickly on because I think I'm actually running shorter of time than I thought, although that was the biggest section. But I want to talk about, again, reasonability, the ability to reason about the code, and evolvability, which is a little bit awkward to say, the ability to change the code over time, or the ease of doing so. Now, this is a big part of my talk on simplicity, but it also usually implies, in my experience, using certain functional programming techniques, which is why I'm so big on that as well. Now, taking a slide from my simplicity talk, really the core of it was this bit that I actually stole from Rich Hickey, his talk, Simple Made Easy, which I reference in that talk, where he goes back to the Latin roots of the word simple and complex, where they mean one fold or braid for simple, or a complex is many folds or braids. You may have heard me talking about this before. This is one of the slides that I reuse the most. So if you've seen it before, you know where I'm going with this. But in the illustration on the left, if you follow one of the strands from the bottom to the top, you should have no problem at all knowing where it ends up. Whereas with the illustration on the right, if you start off with one of those lettered strands and follow to the top, it can actually be quite surprisingly hard to work out where it goes. You really have to sort of follow it around all the way carefully. And there's only 4 strands here. The complexity, what makes it a complex, is that crossing over, that folding or braiding. So if you can think of complexity as things that are interconnecting with each other, particularly in unnecessary ways, that gives us a really good model for what things in our code make it more complex. So here are some of the things that I came up with. Threading and other types of concurrency are perhaps the most obvious one, but also globals or singletons, which are really just globals by a different name. They tie up different parts of your code base to a single point. So it's like a knot in your code. Any other types of shared state will have similar degrees of added complexity, maybe not quite to the same degree, but a long way there. Mutability is another one, which I usually end up having to explain. Really what you are tying together, or compacting, as Rich Hickey likes to call it, is the value of your object and time itself. So as you move through your code, you have to keep re-reasoning about the value of your object by looking at every line of code that it passes through to see whether something changes it. Whereas if something is immutable, you know that once it's set up, that's it. It doesn't change anymore. That frees you up from having to think through all the interactions with the other parts of the code. So that's why mutability is a complexing factor. Cyclomatic complexity, well, it has complexity in the name, but it's just a specific form of complexity, really to do with branches and loops in your code. Now, most code bases, branches and loops are really what make it work. We certainly need cyclomatic complexity, but we can have too much of it as well. So keeping that as low as possible while actually achieving what you need to do is a good idea because it adds extra complexity. And the dependencies, whether dependencies in the code between objects, think particularly about the shared state that we mentioned earlier, or dependencies between modules, and we know how much complexity that adds. These are all things that make it hard to reason about our code. But there's more to it, because it turns out that if you get lower complexity, simpler code, then it's not only easier to reason about, because we can fit it in our head, but it's also easier to test. Again, if you're using TDD or just testing in general, if something is hard to test, it's probably because of unnecessary complexity in the code, or just complexity in general. Sometimes it is necessary. We can't escape that. But unnecessary complexity is something we can do something about. So that's telling you something. And that's why TDD works if you listen to your tests, because they'll tell you where that complexity is, and you can deal with it as it emerges before it sets in. And then it also makes it easier to change. So that's our evolvability. Because things that are unrelated, if they're separate, there's less points you've got to disentangle if you need to change it. So the more, the simpler the code, the less unnecessary complexity, the easier it's going to be to change. And to be honest, the two biggest tools that I found in lowering the complexity of your code, I've already mentioned TDD, for the reasons I said, what the tests tell you, and functional programming techniques. Not necessarily all of it. You can pick and choose. That's why I did the talk Functional C++ for Fun and Profit, where I picked out some of the particular techniques that I found useful. But those sort of approaches, and particularly immutability and correct by construction techniques, are the main things I found really help to lower complexity in the code. So the next intersection to look at is between reasonability, how we can reason about our code, and efficiency, which we said was also related to performance. These things are typically cast as being opposed to each other, or at least a trade-off. And we'll often say that we should make our code readable. We said readable and reasonability, they're similar but not the same, but make our code easy to reason about, we could say, first, and then we measure. And if we need more performance, then we can optimize it. And that optimization will necessarily make it harder to reason about. And there's still truth in that. But, well, actually, why is there a gap in the first place? It's worth looking at that first. So we have a situation where we have a low-level machine, the actual machine that we're targeting, the hardware, that has all these hardware limitations like register sizes and memory and stack size and all those sort of things. And then we have our high-level code, the things where we're creating our pure abstractions that are close to mathematics, shall we say. Great. And then there's this gap in the middle where in order to execute that highly abstracted high-level code, we need to turn it into this ugly low-level code that doesn't perform very well. That's always been the classic situation. And so we sort of carved out this space in the middle for what we call systems languages. Like C was originally designed, or at least called, portable assembler. So something that's close to the machine level, but just abstracted enough that you can move it from machine to machine. Except that machine at the time was the PDP-11. Now, have you ever seen a PDP-11? It's a picture I got from Wikipedia. These are old computers. They're far removed from what we're dealing with today. And of course, we know this story. We told it many times before. Yes, modern processors can trace their lineage back to the PDP-11 in particular, but they're now very different, but especially so when it comes to optimizations. The things that chips do now to optimize how things are run are so far removed from what made sense in the PDP-11 days that we'll often find that techniques that we use to work at that level will backfire on us. So yeah, most naive attempts to outwit the compiler are hopelessly doomed. We know that. So following that easy to reason about and then optimize philosophy, we should also make things easier to reason about by the compiler. That's an interesting thought. So to take some slides again from another one of my talks, the functional programming one this time, I gave this example of a really simple snippet of code that you may have seen something similar to this many, many times. We have a variable, we want to initialize it to a value, but it depends on some condition that we have to evaluate first. And the typical way to do that is to declare an uninitialized variable up front, do the check, and then within the if statement, we'll use a side effect to assign to the variable. When you look at it, it looks straightforward enough. You would think easy to reason about, but there's a number of problems here. We've got that uninitialized variable. Now, we don't like uninitialized variables, but we don't want to initialize it to some default value because that's not going to reflect our intent. But we could insert some code between that initialization and the assignment, and then suddenly things stop working. We also can't make it const. We said that immutability was really important for our ability to reason about the code, because after this block of code, well, we don't know what code that variable is going to move through and how its value may change. We have to look at it all in order to be able to reason about it. So not being able to make it const is a problem as well. Now, if we had what I've called expression-oriented version of C++, like taking cues from some functional programming languages, we could rewrite it something like this, where we treat the if statement as an expression. And now we can initialize our variable directly. We can make it const, there's those side effects, and as a bonus, we can use type inference as well, because now that's all known as well. And in fact, I sort of borrowed that particular example from F#. It has very, very similar syntax to that. But of course, we can do that in C++ today, just using a ternary operator. And so I do actually recommend using ternary operators. They do have problems. They can be quite hard to parse. You need to be careful about that, not overdo it. But for simple things like this, I think that's a great way to actually simplify your code by removing the bits you have to reason about down to the simplest thing. But the reason I brought this up in this context is because my next example was where that breaks down, because we've used a switch statement. And now, well, okay, we don't have a ternary operator that will deal with so many branches. So what can we do? We're stuck with just assigning to an uninitialized variable. So at the time, I introduced what was a relatively unknown technique in the C++ world, but it's now become much more commonplace. The immediately invoked lambda expression, or immediately invoked function expression, which wrap the whole switch statement in a lambda that we immediately invoke at the end, so note those parentheses at the end, and we can return out of it. So while we're still using statements here, we've effectively made this whole thing into a fake expression. We can initialize our variable, we can make it const, we can type inference, all of the properties that we wanted, and it's less characters to type. This is actually less than the previous case, because we've removed those break statements. It doesn't always work out like that, but it does in this case. Now, when I first gave this talk, or the slides this talk was in, I said that I'd check this against some disassemblies, just to prove that it actually generates the same assembly code for enums in this case, and it did. And then I said, if you had a more expensive object, it could actually be better because you wouldn't have that unnecessary construction and then assignment as a separate step. Now, what I didn't have access to at that time was Compiler Explorer. I think it came out while I was giving that talk. So my later talks did reference it. So now I've gone one better, and I have actually got a Compiler Explorer example for this. So I'm just going to quickly share that now. Here, I'll switch my screen over. Compiler Explorer. So down here, you can see our switch statement. Now we've got this expensive class, which is just copying into a vector, but does the job. So it's doing some work on assignment. We have our default constructed version here. So yeah, in theory, if we rewrote this using an immediately invoked lambda expression, it should do less work. So I'm not going to go into this in detail. We're just going to use the number of lines of assembly as a proxy. I think in this case, it works. 255 lines there. Over here, I'm using the immediately invoked lambda expression and 215 lines. We save 40 lines. As I say, it doesn't necessarily mean it's more efficient. In this case, it does work out. So yes, it really is actually doing less work by using this functional technique, the immediately invoked lambda expression. So again, if this stuff matters, in your particular case, you'll always need to check. And it's great that we have tools like Compiler Explorer to make that so easy today. So let me switch back to the slides. Yeah. Okay. I'm running very short of time, actually. I'm a bit surprised. So let's whiz through this. I talked a bit about testing already. Now, property-based testing is another way, we mentioned already, to get at this intersection between reasonability and efficiency. So a very, very quick example. If you have a slow and easy way to do something, and it really works well with algorithms, slow and easy algorithm, easy to verify by inspection, yeah, that's doing what it should do. But then you've got this faster way that's much harder to reason about, but does the same job. Well, you can use property-based testing, and you can do this in Catch, using generators, just to generate values. And then the property is not really a property, it's just verifying that both algorithms produce the same result. And you may need to use a fudge factor in some cases, but this is a great way of verifying a tricky algorithm against a simpler version to get the benefits of reasonability of the slow and easy one and the efficiency of the faster one. So I will skip past that because I've just got a few more things to say. This is what we've looked at. We've looked at 4 intersections: applicability and correctness, correctness and reliability, reasonability, evolvability, and reasonability and efficiency. So you can see there's actually some further intersections between those there. This is really what we've covered. You can get more intersections as well. I'm already out of time. We didn't have that much time to cover more. But the glue that held all these together, hopefully I brought out, were these three tools that we can bring to the party. Use of the type system, use of tests, particularly in the context of TDD, and paying attention to the different error handling techniques, both the runtime I/O side and the logic errors or bugs, really. Different approaches are needed there. So I'm not quite going to have time to sum up with Michael Feather's article. So I'll leave that for the references for you to go and have a look up yourself. And I will just have one more word about Zen. So we had Zen in the title. There wasn't really much Zen in the book, but the original meaning of the word Zen was just meditation. And the article that I didn't show you from Michael Feathers basically concluded that most of the benefits we get are just from paying close attention to the code. And all these different techniques, whether it's TDD or mocking or clean room, or there's a few that he talked about there, really just all amounted to paying close attention to the code. In effect, meditating on the code. The Wikipedia definition for meditating talks about focusing the mind on a particular object, thought, or activity to train attention and awareness and achieve a mentally clear and stable state. So whatever technique we're using, TDD, good use of the type system, paying attention to error handling, they're all forcing us to focus our mind on the code, help to train our attention and awareness on those 6 qualities of software design. And that is Zen, the art of code lifecycle maintenance. I mentioned that link to those references. Excuse me. There's the URL for it. level11direction.com/refs/zen.html. The page is there at the moment. It's not complete. I've got a few more to put in, which I'll do shortly after this, but you can go there as a placeholder. And I've just got time maybe for one question, I think. So looking at the Q&A, why is there a built-in unreachable in the first code snippet? Is it a typo? No, so that was the compiler explorer. I think I won't go back to it now because we're short of time. Without that, because we're doing a switch on an enum, I'll get warnings about not being able to, not having all paths covered. So I'll just put that in to say we'd never get there. Liz is also confused about the difference between property-based testing and fuzz testing. Yes, there is an overlap, but the best way to think of it is that property-based testing, you do more like the unit test level, just directly against parts of your code using specific values, using syntax very similar to unit testing. Whereas fuzz testing is typically from the outside in, end to end. It can be more focused, but it's generally higher level and less specific to the code itself. We can maybe talk about that later when I have more time. But I think I'm over time, so thank you very much for watching, and maybe I'll see some of you in Gathertown. Thank you.